Hello friends, welcome back to my YouTube channel. This is 12th part of my discussion on liquid extraction, and today I will talk about liquid extraction involving insoluble liquids. So in this case, we will be considering a system of three liquids A, B and C. In my previous discussions, A and B were considered to be partially miscible in each other. But in this discussion, we will be considering a system of three liquids A, B and C, in which A and B, they are immiscible in each other. They are immiscible in each other. And in this particular video, I will talk about how to represent the ternary equilibria in this case when you have insoluble liquids. Which are these insoluble liquids? A and B. In my previous discussions, I had considered a system where A and B were partially miscible in each other. And now let us understand how to represent the ternary equilibria when A and B, they are immiscible in each other. And in coming few videos, I will be talking about stage-wise extraction involving such insoluble liquids. So today, the objective of the discussion is to understand the ternary equilibria, to learn how to represent the ternary equilibria. So let us start the discussion. So we are discussing liquid extraction involving insoluble liquids. By insoluble liquids, I mean in the system of three liquids A, B and C, A and B, they are immiscible in each other. So let us begin the discussion. Okay, first let us know the ternary system that we will be considering. So it will be a system of three liquids A, B and C. Out of this, C is soluble in both A and B, and C is the solute to be recovered. A is the carrier solvent and B is the extracting solvent. In this case, A and B, they are completely immiscible in each other. In my previous discussions, these were considered to be partially miscible in each other. Now, we are considering the case where A and B are completely immiscible in each other, and that's why I am calling them insoluble liquids. Okay, so you have a system of three components, three liquids A, B and C. C is the solute. It is soluble in both A and B. But in this case, A and B, they are completely immiscible in each other. These are the insoluble liquids. Now the operation, let us try to understand this with the schematic diagram. So if you add or if you mix the three components in a vessel, agitate the mixture thoroughly and then transfer the mixture to a settling vessel, or you can call settler. What will happen? The mixture will settle into two layers. One will be A rich layer and the other one will be B rich layer. And C will be transferring from A rich layer to B rich layer, and at the same time it will be after there is enough concentration of C in B rich layer, C will then be transferring from B rich layer to A rich layer as well. That means there are two processes. The transfer of C from A rich layer to B rich layer and transfer of C from B rich layer to A rich layer. And when the two layers come to equilibrium with each other, then the rate of transfer of C from A rich layer to B rich layer is equal to the rate of transfer of C from B rich layer to A rich layer. So there is no net transfer of C across the interface between the two phases. And under these conditions, we say that a dynamic equilibrium is reached. Why dynamic equilibrium? Because C is transferring across the interface between the two layers but there is no net transfer of C across the interface. What is the reason for that? The reason is rate of transfer from one phase to the other is same as the rate of transfer from the second layer to the first layer. So if you represent transfer of let us say R represents transfer of C from A to B, RAB, and RBA represent rate of transfer of C from B to A, and at equilibrium these two rates will be equal. The meaning is the amount of C that goes from A to B is exactly same as the amount of C that goes from B to A. So there is no net transfer of C across the interface. So this is a case of dynamic equilibrium. This is the case of dynamic equilibrium. Okay, so you have in the A reach layer, there will be A plus C. There will be no B in it. Why? Because A and B, they are completely immiscible in each other. And similarly, in the B reach layer, there will be just B and C. There will be no A in it. What is the reason? The reason is again A and B, they are completely immiscible in each other. So this is the raffinate layer and this is the extract layer. The raffinate layer will contain all A in it and extract layer will contain all B in it. So that is the different thing when you have such a system where A and B are completely immiscible in each other. That is, they are insoluble liquids. Okay, now let us represent the operation. So the feed solution in this case is A plus C and it is contacted with the solvent phase. Solvent phase, if it is a recovered solvent, it will be containing some amount of C in it. And if it is a pure solvent, then it will be containing just B in it. So you have the operation where feed solution, that is A plus C, is contacted with the solvent phase, which may be pure B and it may contain some little amount of C if it is a recovered solvent. And then these two will be mixed in the mixer, and then the resulting mixture will be transferred to the settler, where the mixture will settle into two layers. One will be the raffinate layer. Raffinate layer will contain A and C, which remains unrecovered. So there is no B in it. All of the A remains in raffinate phase. And you have the extract phase where it will be containing B and the recovered solute C. It will not contain A in it. All of B will remain in the extract phase. So this constitutes one stage where you have a combination of mixer and settler. So all of the A remains in the raffinate phase and all of the B remains in the extract phase. No B goes in the raffinate phase and no A goes to the extract phase. This is possible when A and B, they are completely immiscible in each other. Okay, so let us learn how to when you have such a system, how to represent the ternary equilibria. Let us understand. The ternary equilibria, it is expressed in terms of the weight fraction of the solute on a solute-free basis. So here, instead of using weight fractions of the solute, we are going to use weight fraction of the solute on a solute-free basis. Now, weight fraction of the solute on a solute-free basis. Now, what is this concept? It is defined in this way. Weight fraction of the solute on solute-free basis is equal to weight of solute in the mixture divided by weight of non-solute components, weight of the other components. So, while calculating this weight fraction, weight of the solute is not considered in the denominator. We are just considering the weight of non-solute components. I'm going to tell you in details. For time being, you just understand how weight fraction of solute on a solute-free basis is defined. So this is weight fraction of solute on a solute free basis is equal to weight of the solute divided by weight of non-solute components. In the case of our system, our ternary system, where three components are there, three liquid components A, B and C. A and B, they are insoluble in each other. Feed solution is A plus C. Solute is C. The solute that is to be recovered is C. And solvent, it could be B or B plus C. When is D plus C possible? When you are using a recovered solvent. If you are using a pure solvent, it will be just B. Then the extract phase will be containing B and C, no A in it. All of the B will remain in extract phase, and raffinate phase will contain A and C in it, no B in it. All of A will remain in the raffinate phase. Now weight fraction of C on a C free basis. So we are trying to understand what is weight fraction of solute on a solute free basis. And in our system, C is the solute. So we are understanding weight fraction of C on a C free basis. So such a weight fraction of C on C free basis in the raffinate phase, it will be denoted by capital X. And weight fraction of C on C free basis in the extract phase, it will be denoted by capital Y. So in this case, X will be weight of C in the raffinate divided by weight of non-C, weight of component other than C. And which is that component? The component is A. So in the raffinate phase, it will be weight of C divided by weight of A. That is capital X, weight fraction of C on a C free basis in the raffinate phase. Likewise, in the extract phase, weight fraction of C on C free basis, that is capital Y, it will be weight of C divided by weight of the other component. And which is other component? Weight of B. Because there are just two components in the extract phase, B and C. So it will be simply weight of C divided by weight of non-C, the other component. Which is the other component? Weight of B. And in the case of raffinate, weight fraction of C on C free basis, we are going to denote that by capital X. So it will be weight of C divided by weight of the other component in the raffinate phase. And what is that other component? That is E. Since A and B are completely immiscible in each other, no B will come in the raffinate phase and no A will come in the extract phase. So this is how you define weight fraction of C on C free basis. We are denoting that by X in the raffinate phase and we are denoting that by Y in the extract phase. Now I hope the concept of weight fraction of a solute, how the solute on a solute free basis, it is clear to you. So in our case, weight fraction of C on C free basis in the raffinate phase, we are going to denote that by capital X and it will be defined in this way, weight of C divided by weight of A. And in the extract phase, we are going to denote that by capital Y and it would be defined as weight of C divided by weight of B. And in order to get the equilibrium diagram, what we need to do, we will be plotting capital X on the x-axis. What is capital X? Weight fraction of C on C free basis in the raffinate phase. And capital Y is plotted on the y-axis. What is capital Y? Capital Y is weight fraction of C on C free basis in the extract. So if you plot capital Y on the y-axis and capital X on the x-axis, you are going to get a curve and that will be the equilibrium curve. That will be the equilibrium curve. So this is the equilibrium curve. So in this way, you can represent the ternary equilibria in terms of weight fractions of the solute on a solid free basis. So you just have to plot weight fractions in the extract phase versus weight fraction in the raffinate phase. Of course, this weight fractions will be on a solute-free basis. So you'll be getting a curve like this. And in our analysis of multi-stage operations involving insoluble liquids, we will be using this equilibrium diagram. So that I'll be discussing in my next videos, coming videos. For time being, now you just understand how to represent the ternary equilibria by using these concentrations. Which are these concentrations? Weight fractions of the solute on a solute-free basis. Our next important thing that we will be using, we need to use relationship between small x and capital X. What is this small x? Small x is the weight fraction of C in the raffinate phase. It is simply weight of C. I have defined it, but let me just tell it. Weight of C divided by weight of A plus. That means in the denominator we have considered the weight of C. So it is simple weight fraction of C in the raffinate phase, small x. And what is capital X? We have just understood. This is weight fraction of C on a C-free basis in the raffinate phase. Now our objective is to get relationship between small x and capital X, so that we can use those relations whenever we need to convert small x to capital X or capital X to small x. So let us understand. So capital X, it is defined as, we have just understood the definition. Capital X is weight of C divided by weight of E. Now what I will do, I will divide the numerator and denominator with the total weight of the raffinate phase. So it will be weight of C divided by weight of E plus C, because in the raffinate you have E and C. So the combined weight of E and C will be the weight of the raffinate phase. And in the denominator you have weight of A divided by total weight. So weight of C divided by total weight. So that is nothing but weight fraction of C, and weight of A divided by total E weight in the denominator. So this is weight of C divided by total weight. So that is weight fraction of C, and in the denominator you have weight of A divided by total weight in the raffinate, total weight of the raffinate phase, that is weight fraction of A. So that means X is weight fraction, ratio of weight fraction of C to weight fraction of A in the raffinate phase. Then now I have expressed capital X as weight fraction of C divided by weight fraction of A. So instead of writing it like weight of C divided by weight of A, by simple rearrangement, adjustment, you can express capital X as ratio of weight fraction of C to weight fraction of E. Now since there are only two components in the raffinate phase, which are those two components, A and C? So that means weight fraction of A plus weight fraction of C, it will be equal to 1, as there are only two components, and we know sum of weight fractions of all the components is equal to 1. So from this I can write weight fraction of A is equal to 1 minus weight fraction of C. That means now capital X is written as weight fraction of C divided by 1 minus weight fraction of C. And we know weight fraction of C, we denote it by small x. So that is capital X is equal to small x divided by 1 minus small x. So that is, if small x is known to you, you can get capital X from it. If weight fraction is known to you, you can get weight fraction on solute-free basis. Now if you rearrange this equation, I can just rearrange in this way. I'll bring this term to this side, so it will be capital X into 1 minus x, that is equal to x. That is x minus small x into capital X is equal to small x. That is capital X is equal to small x into capital X plus x. that is capital X is equal to small x into 1 plus x, that is small x is equal to capital X upon 1 plus x. So you get a different relationship between small x and capital X. In this case, if capital X is known to you, or if weight fraction on solute free basis is known to you, you can get weight fraction of solute in the raffinate phase. So these are the relations between capital X and small x. Now in the same way, let us get relationship between small y and capital Y. So now let us get the relationship between small y and capital Y. What are this small y and capital Y? Small y is weight fraction of C in the extract phase, whereas capital Y, we just understood this is weight fraction of C on a C free basis in the extract phase. And how is capital Y defined? Capital Y is defined as weight of C divided by weight of B. Now I'll just make simple change. I will divide the numerator and denominator with total weight of the extract. So that is capital Y is equal to weight of C divided by weight of B plus C, the weight of extract phase, divided by weight of B divided by weight of B plus C. That is individual weight divided by total weight. So weight of C divided by total weight is weight fraction of C. Weight of B divided by total weight is weight fraction of B. So that is capital Y is equal to weight fraction of C divided by weight fraction of B. As there are only two components in the extract phase, weight fraction of B plus weight fraction of C, it will be equal to 1. That is weight fraction of B is equal to 1 minus weight fraction of C. So therefore, Y in this case will be weight fraction of C divided by 1 minus weight fraction of C. Weight fraction of C in the extract phase divided by 1 minus weight fraction of C in the extract phase. But we denote weight fraction of C in the extract phase by small y. So therefore, capital Y will be equal to small y divided by 1 minus small y. So this gives one relationship between capital Y and small y. Now you can have a different relation. This relationship will be useful to calculate capital Y if small y is known to you. Now let us rearrange it. So I'll bring this down on the side. So capital Y into 1 minus small y is equal to small y. That is capital Y minus small y into capital Y is equal to small y. That is capital Y is equal to small y into capital Y plus small y. That is capital Y is equal to small y into 1 plus capital Y. That is small y is equal to capital Y divided by 1 plus capital Y. So in this case, if capital Y, that is weight fraction of C on a C free basis in the extract phase, is known to you, you can find out weight fraction of C in the raffinate phase, so in the extract phase. So with this, I end my discussion for this video. So here we have understood how to represent the ternary equilibria if you have a system of insoluble liquids. That is, out of the three liquids A, B and C, A and B, they are completely immiscible in each other. They are completely insoluble in each other. Then we also learned how to get the relationship between weight fractions on solute free basis and normal simple weight fractions. That is the relationship between capital X and small x, and relationship between capital Y and small y. In my coming videos, I'll be discussing multi-stage. In my next video, I'll be discussing single-stage liquid extraction involving insoluble liquids. So, for now, with this, I will end my discussion for this particular video. Thanks for watching. I hope you have learned how to represent the ternary equilibria if you have insoluble liquids. Thanks for watching. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the like button if you like my videos. If you have any doubts, you please mention them in the comment section. For now, have a nice day. Thanks for watching my video. I hope to see you soon in my next video. Have a nice day. Bye bye.